So as an example, you can think of this. So for an example, let's say, yes, and I'm not going to calculate the thing, but just write it down. Okay. So let A be 1 1 0. Okay, 0 1 0 and 0 0 2. Clear? Now you can easily check that lambda 1 equals to 1 and lambda 2 equals to 2 are two distinct eigenvalues, right? Distinct eigenvalues. You can understand this is a triangular matrix. Eigenvalues. And what are the eigenvectors corresponding to that? And 1 0 0 0 0 1 are the corresponding eigenvectors. So you see here, this is vector. Okay. So you see here, what is happening is this is a deficient matrix essentially. Okay, since we do not have enough information to find out all possible solutions of this problem. Clear? Why? Because if you want to find out, let's say if you consider x prime equals to ax, that problem, then you have two solutions, right? If one considers for this problem, right? If one considers, let's say x prime equals to ax, right? Okay, then what are the solutions? x1 of t given by this matrix, right? 1 0 0 times e to the power t, and x2 of t given by 0 0 1 e to the power 2t. Those are the two solutions. They are linearly independent, of course, but those are the only two linearly independent solutions. Okay, are the only two linearly independent solutions. Okay, but the problem is this is a 3x3 matrix, right? So the solution space is of 3 dimension, and hence you need another matrix to write down the general solution. Yes. So how do you find something like this? That is the main question. Clear? Okay. So what we are going to do is this. See. So our case. Let me put it this way. So setup. Let A be a n cross n matrix. With k less than n linearly independent, Li is linearly independent here, eigenvectors. Okay, vectors. Okay, so now the thing is this, of course, what do we have? One has, so let us remind us, one has k linearly independent solutions. Okay, right, of the form e power lambda t times v, right? So there are k linearly independent solutions. Okay, now to find general solution, what do you need? Solution, we need to find, okay, the additional n minus k linearly independent solution. Okay, to find additional n minus k linearly independent solution. Clear? Okay, so how do we get something like this? Let's just understand this. Okay, so I hope you remember matrix exponential, which we did last week. Okay, so we are going to use that sort of fact. Okay, see, we know that x prime equals to ax. Yes, what is the solution of this problem? Yes, it is given by any solution. Okay, let me write it this way. Any solution of x prime equals to ax, okay, must look like xt, which is e to the power at times a constant c. It's a n cross 1 constant matrix, right? N cross 1 constant vector or matrix, whatever you want to call it, essentially constant. Okay, right. Now you see, the thing is this, what we can do is we can manipulate this thing a little bit. Yes, what is the manipulation? So what we will do is this. So we will see now that how we can find n linearly independent vectors. Okay, so what we do is, therefore observe e to the power at. Yes, see, if we can find e to the power at, we are done, right? Okay, of course, if you can calculate the matrix exponential, that is fine. That is, you can do it directly. That's okay. But the thing is, most of the times it is, you have seen that it is actually a little complicated to calculate it. Okay, in most of the cases. So this is a the method of eigenvectors values is better way of dealing with it. So e power at, we can write it like this. See, e power a minus lambda I times t, okay, and e power lambda I t, clear, times a vector, let's say c vector is there, so that c vector is always there, clear, the c vector is there. So we can write it like this. See, if we write it like this, a minus lambda I t is nothing but, that this is the part which we comes up when we are dealing with the eigenvalue problem, right? So that is why we wrote it like this. Okay, now for any lambda we will write it this, and why can we do it? You see, since we can do it, since a minus lambda I times lambda I is commutative, these two matrices are commutative, so lambda I times a minus lambda I, right? We can do this. Yes, and you see, also e to the power lambda I t, yes, acting at a matrix C. What is it? It is nothing but, let's just write it down, I plus lambda I t plus lambda square I square t square by 2 factorial up till infinity times c, right? Times c. Okay, now you see, if you multiply this thing, what is the lambda part? Lambda part is here, right? Okay, so this is nothing but, if you write it properly, this is nothing but 1 plus lambda t plus lambda square t square by 2 factorial t square by 2 factorial plus, I can write it like this, right, times c. See, identity times c is c, so I am writing that matrix C as 1 times c. Is it okay? C, identity times c is the matrix C, n cross 1 matrix, whatever it is, but n cross 1 matrix C, right? Identity is n cross n. Okay, now you see, this matrix C is nothing but 1 times c. 1 is the scalar in R. So we are using that fact here. Yes, if you do that, see, what is this? This is nothing but e power lambda t times the matrix C. Okay, therefore e power lambda t times the vector C is nothing but e power lambda t. See, this is real. Yes, e power a minus lambda I times c. Is this okay? Right? So one matrix exponential, we just wrote it as a scalar, and the other part is the matrix exponential part, right? Okay, now a crucial observation is this. A crucial observation, what is it? See, that if V satisfies a minus lambda I power n times v equals to 0, right? If v satisfies this for some m, let's write it, for some m in n, right? Then the series, yes, then the series e power a minus lambda I t times c, that terminates, right? That terminates after m terms, right? That is very easy to see. Yes, so, and if this is 0, and also a minus lambda I times m plus l is also going to be 0, right, for all L, Clear? In n. So if A minus lambda I whole power m, that matrix is going to be 0. Then if you increase the power, right, with 1 or 2 or whatever, m plus l that is, then that is also going to be 0, right? I hope this is clear. Why? I mean, please check this part. This is not very difficult to see. Of course, it is true. Okay, so please check this part. Okay, so now therefore, what happens? You see, e power a minus lambda I times t acting at the vector c, that will be nothing but v, clear, plus t times a minus lambda I times c. Okay, sorry, it is v, it is c plus this, so identity times c plus it will go on, and then I have t power m minus 1 by m minus 1 factorial, okay, a minus lambda I to the power m minus 1 times c. Clear? That's what we have. See, we have assumed that if you have a v, if you can find a v, okay, we don't know whether such a v exists or not. If we can find a v such that happens, okay, then what? Okay, I should write it as c. It will be better. I think it should be better. Okay, or maybe v is okay. No, okay, maybe write it as c. So basically, I am trying to find a m such that a minus lambda I whole power m, that is going to be a 0 matrix essentially. Okay, so that matrix acting on any vector c is going to be 0. So it's not a problem. Okay, we'll just write it like this. Clear? Okay, and then what happens is, you see, e power at times c. What is it? It is nothing but e power lambda t. You remember? You see, we wrote it like this: e power lambda t, e power a minus lambda I times c, right? And you have e power a minus lambda I t times the vector c. Yes, so let us write it properly. It is e power lambda t, and then I have the vector c plus t a minus lambda I times c plus it will go on, and I have this last term, this term, by m minus 1 factorial a minus lambda I power m minus 1 times c. Okay, see, this is the algorithm essentially to calculate e power at times c. Once we do that, then we are done, right? So what does this suggest? Can we find any linearly independent solution? Okay, so the algorithm looks like this. Algorithm, RITHM, let's just put it this way, algorithm. How does it look like? Okay, so first of all, A. So first of all, you find all the eigenvalues and eigenvectors of A, of course. So find all the eigenvalues and eigenvectors of A, and eigenvectors of A. Clear? So you start with that. So first find everything. Yes. See, if it has n linearly independent eigenvector, of course you have the full set, right? So it's not a problem. Okay. Now, so in that case it's done. If so, basically number B. If A has only, let's say, k which is less than n linearly independent eigenvector, okay, then what happens? Then we have only k linearly independent solutions, right? Solutions of the form, what is the form? E power lambda t times some vector v, okay, which is just the eigenvector, basically corresponding eigenvector, right? Now how do you find the additional solutions? So to find the additional solutions, what we do is this: we pick an eigenvalue lambda, we pick an eigenvalue lambda, right? Okay, we pick that eigenvalue, and find all eigenvectors okay, for which a minus lambda I square v is going to be 0. Is this okay? V is going to be 0. This is what we are trying to find, if it is possible. Okay, so we do that. But of course, a minus lambda I times v should not be 0. So basically, it should not be a eigenvector as, I mean, not like in the usual sense a minus lambda I times v has to be 0. That is not 0, but the square part is 0. Right? And you see, for such a vector v, if you can find such a vector, let's say vector v, okay, what you have, e power at times v, okay, that can be written as e power lambda t e power a minus lambda I times t acting at v. Clear? V is some vector, it's a constant vector which initially we were writing at c, now I'm just writing it v, doesn't matter. Okay, and this is nothing but e power lambda t. In this case, what happens? It will be v plus t times a minus lambda I times v, right? Because the square term, everything is going to be 0, right? So we won't have this. So this is what, okay, so this will be is an additional solution, okay, additional solution of x prime equals to ax. Clear? So that will be an additional solution. Okay, and we do it for all other eigenvalues, and so we do it for all other eigenvalues. Okay, so do it for other eigenvalues also, if it is possible. Okay, right. Now this actually, the second step actually should give you all the possible whatever the solutions you are going to get. So the a, b, c, right, b, c. Okay, the third step. So if we still does not have enough solutions, linearly independent solutions, that is, okay, enough solutions, we find all vectors v, okay, v, such that a minus lambda I cube v is 0, but the square is not 0. Square v is non-zero. Is this okay? So for such a v, for such a vector v, okay, what do you have? E power at times v is nothing but e power lambda t v plus t times a minus lambda I times v plus t square by 2 factorial a minus lambda I square v. Clear? The cube part and then the corresponding the other the large powers, they are going to be 0, right? So that is there. So this is an additional solution of x prime equals to ax. Clear? Okay. So, and the thing is, essentially, in a worst case scenario, we continue doing this and we hopefully obtain n linearly independent solution. Okay. So we keep proceeding to obtain n linearly independent solution. Okay, Now you may ask that what is the guarantee that this will work, this procedure should work, and it is going to give us any linearly independent solution. Okay, why should it be? Okay, so for that there is a theorem in linear algebra. I am not quite sure. I will not be doing this proof of the theorem, but what I can do is this. Essentially, I will just write down the theorem, so you can get it in any standard linear algebra book. So basically you can look at Lang or any other book. Okay, so most standard linear algebra book will contain this result. So what does it say? So let the characteristic polynomial, okay, so I am not writing everything is in detail. CP, characteristic polynomial of A, let's say, have k distinct roots. Okay, distinct roots. Okay, what are the roots? Lambda 1, lambda k. Yes, with multiplicities, what are the multiplicities? Let's just call it n1, nk respectively. Okay, what does it mean? It means that p lambda, the characteristic polynomial, it will look like this: lambda 1 minus lambda whole power n1 and lambda k minus lambda whole power nk. Okay, this polynomial can be factorized into this. Okay, now suppose A has only Vj, okay, which is less than Nj. Yes, linearly independent solutions. Okay, if it has solutions with eigenvectors. Sorry, I should not write solutions. Linearly independent eigenvectors. Okay, with eigenvalues lambda j, Okay, this is what our assumption is. Then what we can say is, then the equation A minus lambda j I times square v equals to 0 has at least how many solutions? If this has Vj, then it is Vj plus 1. Linearly independent solutions. Clear? Yes, I hope this is clear. So what it is saying is, corresponding to lambda j, if there are Vj linearly independent solutions, so basically A minus lambda ji, V equals to 0. If that happens, okay, and there are like a Vj linearly independent solution, then the square will have one more, Vj plus 1. Okay, and essentially what you can say is, more generally, let me put it this way, more generally, okay, if A minus lambda I whole power m, let's say, okay, lambda ji, so corresponding to the lambda jth eigenvalue, okay, has equals to, sorry, by mistake I should write it like this, equals to z, has, okay, only mj, okay, which is less than nj. Clear? Linearly independent solutions. If this equation has linearly independent solutions, mj which is less than, then the equation A minus lambda j I, okay, and then you see, let's just put it this way, that m plus 1 times v equals to 0, okay, has at least mj plus 1 linearly independent solutions. I hope this is clear. What it is saying is this: you see, if A minus lambda I times v is 0, if that has, let's say, 5 solutions, then A minus lambda I times square v equals to 0 will have 5 plus 1 6 solutions at least. Okay, that's at least. Okay, so if A minus lambda j times I, okay, time whole power m equals to 0, that equation, let's say, has mj linearly independent solution, then if you take m plus 1 power, then it will have mj plus 1 linearly independent, at least, okay, it is very important, at least mj plus 1 linearly independent solution. Okay, so from this lemma you can actually see this lemma. So basically what we can say is this: from the theorem, one can say, one may deduce, okay, that there exist integers, okay, there exist dj which is in n, with dj less than nj, clear? Okay, dj of course can be less than equals to, such that a minus lambda j times I, okay, to the power dj, okay, acting at v equals to 0, has at least nj linearly independent solutions. Clear? That is always there. So thus, for any eigenvalue lambda j, so for any lambda j eigenvalue ev of a, okay, we can compute nj linearly independent solutions of x prime equals to ax, right? X prime equals to x, and all these solutions will have, okay, and all these solutions x of t and x of t will look like this: e power lambda j t, then the vector v plus a t times a minus lambda j I times v plus, and it will go on doing t to the power dj minus 1 by dj minus 1 factorial a minus lambda j I power dj minus 1 times v. Clear? And if you can also show that, and moreover n1 plus n2 plus nk, this will be n solutions. So this will actually be the full set of n solutions are linearly independent. Okay, this can be done. So this is, all of this is basically from the linear algebra, from any standard linear algebra book, Hopman-Kunz or Lang, you can get it. Okay, so please do that. But the thing is, essentially this is how we actually calculate the this repeated eigenvalue thing. Okay, so this is a little complicated, but we can do it like this. Okay, so as an example, let me do it an example, so it may become clear. Okay, so example. So let's say x prime equals to 1 0 0 1 1 0 0 0 2 times x. Clear? Okay. So the characteristic polynomial, if you solve the characteristic polynomial, the roots, therefore the roots or the eigenvalues which you are going to get. So lambda, let's say 1 2, okay, repeated eigenvalues are 1, and lambda 3, let us just call it as 2, not let us just, but it will be 2. So you can check this part, so please do that, go on and check this. Clear? Okay, so first of all, for lambda equals to 2, right, for lambda equals to 2, this is just a distinct eigenvalue, so we let us find the eigenvalue. So for lambda equals to 2, okay, what do I need to do? I just need to check a minus 2i times v. Okay, so we need to find a non-zero v. Let me put it this way: we need to find a non-zero v such that a minus 2i times v, okay, which if you calculate here, it will be 1 minus 2 minus 1, this is 1, this is 0 times, this is 0, this is minus 1, this is 0, and this is 0 0 0, right? Okay, 2i 0 0 0. So now v1, v2, v3 has to be 0 0 0. Clear? Okay, so therefore if you put it this way, then v1 equals to v2 equals to 0 if you solve it, right? v1 equals to v2 equals to 0, and v3 is arbitrary. v3 is arbitrary. Okay, this is trivial to see. This is trivial. Minus v1 plus v2 equals to 0. v1 and v2 are basically same, and v2 is 0 from the third equation. So basically v1 and v2 is going to be 0. Clear? Okay. So what is the one solution which you are going to get? Therefore, one solution. Let's call this x3 of t. Okay. It will be e to the power 2t times the corresponding vector, and the corresponding vector we will choose it at 0 0 1. Clear? Okay, now what happens is we need to find what is the vector corresponding to lambda equals to 1. Okay, so for lambda equals to 1, okay, we seek a non-zero vector, v such that a minus lambda I times v, which is nothing but, here it is 1, right? Lambda is 1. So 0, 1, 0, 0, 0, 0, 0, 0, 1 times v1, v2, v3 is nothing but 0, 0, 0. Clear? Okay, this will imply v2 equals to v3 equals to 0, and v1 is arbitrary. Okay, it's trivial, right? You see, v2 equals to 0, v3 equals to 0, v1 is arbitrary. That's what we are getting. Okay, so therefore, what is the first solution which you are getting? x1 of 3. It is e power t, and then the, you see, v2, v3 0. So this is 1 0 0. This is one solution. Okay, so x1 is one solution, x3 is another solution. Where is x3? x3 is another solution. Okay, so third solution, I need to find another solution, and then that will give us a general solution. Okay, how do I find the next solution? Okay, so the question now is how to find the third linearly independent solution. That is the question. Okay, so let's do it in the next page. Okay, so what did we tell you? You see, since A has only one linearly independent eigenvector corresponding to the eigenvalue 1, we look for other solutions of this equation. Basically, A minus lambda I square, okay, V, and here lambda is 1. Okay, see, lambda equals to 2 won't give us any other solution. That is already done. Lambda equals to 1, it is multiplicity 2, right? So we expect this to get give us another solution. So basically, we do not look at a minus lambda I times v anymore. We look at a minus lambda I square v. Okay, and if you calculate it, it becomes 0 1 0 0 0 0 0 0 1. This is a minus lambda I. You see, a minus lambda I. Okay, and times 0 1 0 0 0 0 0 0 1 times v. Okay, which you calculate, it becomes the first one 0 1 2, right? 1 2 is 0, and 1 3 is 0, right? 0. Okay, so the next column is again 0 0 and 0, right? The third column is 0 0, and 1 times 1 is 1. Okay, times v1 v2 v3 is nothing but 0 0 and 0. Clear? So this will imply that v3 equals to 0 and v1 and v2 are arbitrary. Okay, you can choose whatever you want. So therefore, the vector which you are choosing here, let's just choose it to be, this is 0. V1, V2 is arbitrary. So let's just choose it to be 0, 1, 0. Clear? Okay. So you see, therefore, this V if you are choosing, let's call it V tilde. Then A minus I, lambda is 1 here, right? See, lambda is 1 here. Okay, A minus I square V cap, this is 0. But you can check that A minus lambda I times V cap is non-zero. Okay, so please check this part. Check. It's very trivial to see, but anyways, please check it. Okay, so therefore, what is the solution? See, therefore, x2 of t, it will be, you remember, e power at, clear, times 0, 1, 0. Right? That's the solution, right? You see, for this vector, this is any given vector, right? But the thing is, the special part is a minus lambda is square times v cap is 0. Clear? And I know that e power at times any vector will be a solution of this problem, right? So that vector I am choosing it to be 0, 1, 0. Is it okay? Now you see, this is nothing but if you have to do it this way, okay? E to the power lambda t, lambda is 1 here, so it is pure t, and then we can write it as e power a minus I times t. You remember, we can just break it up, and then I have this vector 0, 1, 0. Clear? So if you write it properly, it is e to the power t and then identity plus t times a minus I, okay, and then our vector 0, 1, 0. Okay, so if you now calculate it, it is e to the power t. Now let's just calculate this thing. It is 0, 1, 0 plus t times 0, 1, 0, 0, 0, 0, 0, 0, 1 times 0, 1, 0. Clear? So if you write it properly, it becomes e to the power t 0, 1, 0. I hope this is correct. So please check this part. I think my calculation is okay, but anyways. Okay, so it becomes this, right? So this is e to the power t, it becomes t 1 and 0. Okay, if you write everything properly, this is what we end up with. So this is, and you can see, of course, this is independent of it. So this is the second, so x2, second linearly independent solution. Okay, so how do you find the general solution? You write x to be c1 times x1 plus c2 times x2 plus c3 times x3, and then you are done. So you understand what's going on, okay, how to do this calculation. So anyways, what I want you to do is, please work out a problem. I will put it in assignment. Work out a problem and see how this is done. So with this, I am going to end this video.